Good morning, students. Yes, Physics 12, 4 chapter completed. Chapter 1, Electric Charges and Electric Field. Chapter 2, Electrostatic Potential and Capacitance. Yes, Chapter 1 and 2, they are called electrostatics. Chapter 3, that is current electricity when charge is flowing. Okay, so what is characteristics of that? Chapter number 4, magnetic properties of current. Okay, due to current, due to flowing charges, what is magnetic effect? And yes, in last lecture, in last chapter, we have proved, okay, when charges are flowing, means due to current, magnetic field is produced. Magnetic field is produced. And one theory we have proved, okay, magnetic circular current carrying coil. Circular current carrying coil. It behaves as magnetic dipole. Circular current carrying coil. It behaves as magnetic dipole. So yes, in this chapter, now we will study about chapter number 5, that is magnetism and matter. In last lecture, in last chapter, we have discussed current carrying coil behaves as magnetic dipole. But in nature, there are some material which behaves as magnet, Why they have some magnetic properties? Some objects behaves as magnet, or some can be converted in magnet, and why not others? Then why? That we will study in this chapter. Now, magnetism and matter. In this chapter, we have to study about magnetism and matter. Okay, magnet. What is magnet? So yes, that magnet word comes from an Icelandic Greece called magnesia, in which Shepherd complained that their iron stick and their shoes nails, okay, they stick with some pores. They attract that objects with it. So yes, from that thing, that word comes, that is magnet. Yes, in past also some Chinese, they also use magnetic needle to find direction in desert. Okay, so yes, in past they have used, or from some experiment, from some experiences, they concluded that yes, there are some material which attracts iron and similar objects towards it. Okay, and also for some material there is repulsive force. So yes, after numbers of experiment, after numbers of studies, they gave some conclusion. And here the first theory of this chapter is some commonly known ideas regarding magnetism. Okay, see, first point. The earth behaves as a magnet with magnetic field pointing approximately from geographical south to north. Yes, Earth, we know that it is North Pole, it is South Pole. Okay, so yes, Earth behaves as a magnet with a magnetic field pointing approximately from geographic south to geographic north. I mean, magnetic field lines is from geographic south to geographic north. Okay, like this. Clear about this? So yes, it is first point that you have to remember. The earth behaves as a magnet with magnetic field pointing approximately from geographical south to geographical north. Yes, for this point we will discuss in this chapter. Okay, Earth's magnetism or magnetic elements of Earth. We will discuss in brief. Okay, why this magnetic field lines is from geographical south to geographical north. Okay, yes, we will discuss about this point. Second point is, when a bar magnet is freely suspended, it points in the north-south direction. If I have bar magnet like this, and if I freely suspend it, then it will point in north and south direction. It will point in north and south direction like this. Okay, it will point in north and south direction. The tip which points in geographical north, it is called north pole of magnet. It is called north pole of magnet. And similarly, the tip which points in geographical south, it is called south pole of magnet. It is called south pole of magnet. So whenever we have a bar magnet or magnetic needle like this, okay, if we have a magnetic needle which is suspended freely, okay, then yes, it points in north-south direction. The tip which points in geographical north, it is called North Pole and it is called South. Clear about this? Yes. So yes, the tip which points to the geographic north is called North Pole and the tip which points to the geographic south is called the South Pole of magnet. Third point is, there is a repulsive force when two north pole or south poles of two magnets are brought closer. Yes, we know that between two like poles there is repulsive force. Between two like poles there is repulsive force. But there is an attractive force between the north pole of one magnet and south pole of other. Means between two unlike poles there is attractive force. So yes, you know this. Between two like poles there is repulsive force, between two unlike poles there is attractive force. Okay, next one is, we cannot isolate the north or south pole of a magnet. We cannot isolate the north or south pole of magnet. It means if bar magnet is broken into two halves, we get two similar bar magnets with some weaker properties. Unlike electric charges, isolated magnetic north and south pole known as magnetic monopoles do not exist. Magnetic monopoles do not exist. Now what is meaning of this? See, if you remember, what is electric dipole? Electric dipole is if I have two charges, minus q and plus q charges. It is called electric dipole. But if I am taking distance between two electric charges very large, then yes, I can say that these minus q and plus q charges, they are isolated. They are isolated. Clear about this? So yes, electric monopoles are possible. Electric monopoles do exist. But if I have a magnet like this, see, if I have a magnet like this, it is north pole and it is south pole. And if I cut this magnet in two equal halves like this, if I cut this magnet in two equal halves, then yes, each part behaves as magnet. Each part behaves as magnet, but having some weaker strength. Clear about this? Having some weaker properties. Okay? So yes, in this magnet we have two poles, north pole and south pole. If I cut this magnet into equal halves, this part and this part, they also behave as magnet. Magnet means having two poles, north pole and south pole. North pole and south pole. Clear about this? Clear about this? So yes, unlike electric charges, isolated magnetic north and south poles known as magnetic monopoles do not exist. Okay, they are always in pair. They are always in pair. If this end is north pole, then this end is obviously it is south pole. Clear? If I cut this magnet into equal halves, means it is only north pole, it is only south pole. No, it is wrong. It is wrong. This magnet, this part, it also behaves as magnet having north pole and south pole. Clear about this? So yes, when we cut a bar magnet into equal halves, we will get two similar bar magnets with some weaker properties. Okay, clear about this? Again, electric monopoles are possible. Plus q minus q. If I am taking distance between them very large, they behave as monopoles. But magnetic monopoles are not possible. Magnetic monopoles are not possible. Clear about this? Okay. For our last point is, it is possible to make magnets out of iron and its alloys. See, if you remember chapter 2, polarization. Between two plates of capacitor, if we place any dielectric, then it is polarized. It may be polar or non-polar. It is polarized, means electric dipole moment of each and every molecule aligns in direction of electric field, and thus it is polarized. Similar theory we will study in this chapter. If I have solenoid from which current is flowing, okay, and now if I place iron core or of some alloy in this solenoid, then yes, this iron core is magnetized, and it is called magnetization. and it is called magnetization. Remember polarization from chapter number 2. Remember polarization from chapter number 2. Here it is called magnetization. Okay, we can convert iron or its alloys in a magnet. Clear about this? So yes, it is all about some history, okay, and some commonly known ideas regarding magnetism. First point, Earth behaves as magnet, magnetic field lines from geographical south to geographical north. Second, if bar magnet is suspended freely, it will always align in north and south direction because magnetic field of Earth is in north-south direction. Okay. Third one is, yes, between two like charges there is repulsive force, between two unlike charges there is attractive force. Fourth one is no magnetic monopoles are possible. Electric monopoles are possible. And last one is, it is possible to make magnets out of some iron and its alloys. Yes, we will see this method in detail. So from such all points, in this chapter we have to discuss about this each and every point in detail. Clear about this? Now magnets. Yes, chapter's title is magnetism and matter. So we know that some material behaves as magnet. Okay, so types of magnet. Yes, there are numbers of types of magnet. But in this chapter we will study bar magnet. In this chapter we will study bar magnet like this. It is North Pole and it is South Pole. And solenoid. Bar magnet and solenoid, because solenoid means current carrying coil, and in last chapter we have proved that current carrying coil behaves as magnetic dipole. Yes, I can consider this magnet as magnetic dipole. Why magnetic dipole? Each and every magnet has two poles, north pole and south pole. So yes, I can say it is magnetic dipole. Clear about this? Why magnetic dipole? Because it has two magnetic poles, north pole and south pole. Okay, so now in this chapter we will discuss about bar magnet and solenoid. First of all, we will study about bar magnet. Okay, bar magnet. Yes, what is bar magnet? You know what is bar magnet. Okay, and in reverse conductor, if you have observed one experiment, that is when we take bar magnet, a glass is placed over it, and if we sprinkle iron fillings, iron dust, iron particles on that, and if we tap that glass surface, then we know that iron fillings are arranged like this. Okay, that iron fillings are arranged like this. Okay, yes, you know this experiment, or you can also perform this experiment at home. So yes, it is one experiment. Okay, when iron fillings sprinkled on a sheet of glass placed over a short bar magnet, the arrangement of iron fillings is as shown in figure like this. And yes, from this experiment there are some points. See, the pattern of iron filling suggests that the magnet has two poles. How two poles? See, at these 2 points, we can see from figure. Okay, yes, at these 2 points, each and every line, each and every particles, they are congested or they are more in this region. Means these 2 points are called poles. Okay, remember electric dipole. Electric field line starts from positive charge and ends in negative charge. So at that two charges, numbers of electric field lines are more than other region. Okay, so yes, here the pattern of iron filling suggests that the magnet has two poles similar to positive and negative charges of an electric dipole. Yes, one pole is termed as north pole and another pole is termed as south pole. Clear about this? So yes, it is about bar magnet. When iron filling sprinkled on a sheet of glass plate over a short bar magnet, the arrangement of iron fillings is as shown in figure. Yes, it has two poles, one north pole and one south pole. Okay. Next, this pattern pattern of iron fillings suggest magnetic field lines. Suggests magnetic field line. Okay. So next point is the magnetic field lines and its properties. The next point is magnetic field lines and its properties. So see, what about magnetic field lines and its properties? Here it is. Here it is. From this pattern, we can say, yes, if I have a bar magnet, if we have a bar magnet, it is south pole, it is north pole. It is axis of magnet. Okay, so yes, from this pattern we can say that, or from experiments it is proved that magnetic field lines starts from north pole moving towards south pole, and inside magnet it is moving from south to north. Inside magnet it is moving from south to north. Again, in outside magnet, magnetic field lines emerges from north pole, enters in south pole, and yes, again inside magnet it is moving from south pole to north pole. It is moving from south pole to north. South pole to north. Clear? On axis, magnetic field is in this direction. On axis, magnetic field it is in this direction. So see, here we can say magnetic field lines emerges from north pole, moving towards south pole, and from south pole to north pole. Means it forms a closed loop. It forms a closed loop. So yes, first point to be remembered is the magnetic field lines of magnet form continuous closed loop. Form continuous closed loop. Okay. While in electric field lines, they never form closed loop. Electric field lines, they never form closed loop. It starts from positive charge and ends in negative charge. It starts from positive charge and ends in negative charge. While in this case, it forms a closed loop. Okay, so yes, it is first point. The magnetic field lines of a bar magnet forms closed loop. Second point, yes, the tangent to field lines at a given point represents the direction of magnetic field at that point. Suppose I want to find what is direction of magnetic field at this point, then it is in direction of tangent. At this point, it is in direction of tangent. At this point, it is in direction of tangent. Clear about this? So yes, you know this point. Remember electric field lines, electric field. The tangent to the field lines at a given point represents the direction of magnetic field at that point. Okay. Next one is, the larger the number of field lines crossing per unit area, the stronger is the magnetic field. See, for example, if in this region A, I have one surface like this. In this region B, I have one surface like this, having unique area. Then simple, from this area A, numbers of field lines passing more, from this less. So obviously, in this region, magnetic field is strong, while in this region, magnetic field B is weak. Magnetic field B is weak. Clear about this? So yes, the larger the number of field lines crossing per unit area, the stronger is the magnetic field. In this region, magnetic field is stronger, while in this region, magnetic field is weaker. And yes, as magnetic field here, B is not same. It is called non-uniform magnetic field. It is called non-uniform magnetic field. Why? In such cases, see, if electric field lines are like this, in this region and in this region, yes, E is same here, magnetic field B is same. So it is called uniform magnetic field. It is called uniform magnetic field. Clear about this? So yes, non-uniform magnetic field and uniform magnetic field. Okay, last point, the field lines do not intersect. The field lines do not intersect. And if they intersect, I have two field lines. Yes, remember this point. The tangent to field lines at a given point represents the direction of magnetic field at that point. If they intersect at this point, due to this magnetic field line, tangent, it is in this direction, P. Due to this magnetic field line, tangent, it is at this point. So, for a same point, we have two direction of magnetic field. Is it possible that at the same time I am facing north and south, both direction? No, it is not possible. So at a time, two direction of object or particle is not possible. So yes, is not possible. The magnetic field lines do not intersect. The magnetic field lines do not intersect. Clear about this? So yes, in this lecture we have studied about some commonly points regarding magnetism, then the bar magnet, and then the magnetic field lines and its properties. Clear about this?